The goal of this project was to design and create a wing section out of foam board, following an iterative design process. This task was set with parameters of limiting the mass, preventing failure under a load factor of 2, and withstanding bending and torsion constraints.
The design cycle is an iterative process comprising of conceptual design, preliminary design, detailed design, and acceptance and reevaluation. Once the process is complete, improvement upon ideas and rectifying mistakes leads us back into the cycle to improve our design.
Conceptual design. We started out sketching the parts required to make our wing. These included the leading edge, spar, trailing edge, control surfaces, and ribs. This led us to using a stressed skin design over the outside of the wing to more evenly distribute load while reducing the mass. We also had to grasp beam theory when designing our spar, the main load-carrying component. We undertook structural analysis by modelling it as a cantilever beam, plotting shear force and bending moment diagrams. Then, using the equation shown, we could also find the bending moment M by using the second moment of area, the local stress, and the distance from the neutral axis.
It is vital to understand the difference in bending and torsion to fully understand these results. As you can see, bending is a result of evenly spaced forces acting in the same direction and acting a curve on the material, whilst torsion is the rotational force applied about the center axis of the beam. For the preliminary design, from here, we began to use Excel sheets to further analyze how our spar would act under a load factor of 2. By changing the dimensions of the spar, we could test their direct strength and torsional compliance accordingly. We observed that under given point load, the beam's deflection increased with length until the maximum predicted deflection of 42.7 millimeters. Once we were happy with our beam's cross-section, we could adjust its positioning in the aerofoil to ensure it fit.
Detailed design. We then created the wing in SolidWorks, running simulations of both bending and torsion. We focused mostly on analysing the spar, as this component takes the majority of the load. Like in Excel, we could determine how much the beam is predicted to deflect under our load factor, getting a value of 47.9 millimeters. To make sure this value is accurate, we created foam board in SolidWorks, importing the material properties used for calculations.
The final stage of our design process is practical testing and acceptance. In the lab sessions, we constructed spars according to the designs we had acquired on Excel and through iterative models on paper. With these spars, we tested for deflection and torsion using massed loads at the tip, and we measured the displacement under increasing load. Using this acquired data, we formatted graphs of force against displacement and angle of deflection against moment, seeing a linear pattern in both as expected.
To further understand the beam's ultimate tensile stress, we of course had to add mass until failure. After we finished testing the spar, we created the rest of the wing, and then reviewed the mass distribution for the completed project.
Now that we have accepted our design and understand the theory, we can go back to the drawing board of conceptual design and look to improve our spar. A few ways in which we thought we could do this is by tapering the beam or cutting circular holes near the tip to reduce mass whilst not compromising the structural stability in place.
Thank you for watching our iterative design process of building a wing.